Now we're going to look at what happens when we try to add up all of the terms in an infinite geometric series. Sometimes it's possible, sometimes it's not. If it's possible, we call it a converging geometric series. If it is not possible, we say it is a diverging series. So we're going to look first at a converging geometric series. We have the series 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus dot dot dot. So this is an infinite series, goes on forever. Notice that each term is half as big as the previous term. If we do 1/2 times 1/2 is 1/4 times 1/2 is 1/8 times 1/2 is 1/16. So this is a fairly simple one, just as an example. So r is 1/2. Remember, if you get a complicated one that you cannot figure out, you take the second term divided by the first, the third term divided by the second, and so forth to find r. So r is 1/2 here. We're going to look first at some of the partial sums. So we know s sub 1 is 1/2. S sub 2 is 1/2 plus 1/4, which I hope you realize equals 3/4. S sub 3 is 1/2 plus 1/4 plus 1/8. Well, that's 3/4 plus another 8/8. 3/4, 6/8 plus 1/8, 7/8. S sub 4 is equal to 7/8 plus 1 over 32. No, 1 over 16, I'm sorry. 1 over 16. So that would be 14/16 plus 1/16 is 15/16. S sub 5, if we go through the same process, is equal to 31 over 32. You can check that out for yourself. So notice we have 1/2, 3/4, 7/8, 15/16, 31 over 32. If I asked you, what do you think will happen when we keep adding more and more terms? This number appears to be getting closer and closer to 1. So sum is approaching 1. At least that's what it appears to be. So let's take a look at our sum formula. We have the sum formula that says S sub n is equal to a sub 1 plus 1 minus r to the n over 1 minus r. Well, let's think what happens to this term right here if r is 1/2 and n is very big, and as n goes to infinity. So as n goes to infinity, so you might even try in your calculator putting in 1/2 to some very large exponent, 1/2 to the 100, 1/2 to the 1000. I think you would realize that it's going to get smaller and smaller and smaller because we have 1/2, 1/8, 1/16, 1/32, so forth. That's going to turn out to be a number close to 0. So as it gets infinitely big, this term basically disappears, becomes close to 0. So what we have here is s. Notice no n because this is an infinite number of terms. S is the limit as n goes to infinity of s sub n, and it equals a sub 1. I'm going to write this a little better, so a little more neatly so you can see this more clearly. Sorry. S is equal to the limit as n goes to infinity of s sub n. So in other words, as we get infinitely many terms, what does that sum approach? And that's equal to a sub 1 over 1 minus r. So here's our infinite sum here. So all what happens is the 1 minus r to the n just becomes 1 because r to the n gets closer and closer to 0 with a small value of r. So in this case, we would say, in our example, I'll use blue here, using a sub 1 is 1/2, and r is 1/2 in this situation. So s equals the limit as n goes to infinity of s sub n, and that equals 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which equals 1. So we actually say that the infinite sum equals 1. With an infinite number of terms, it actually equals 1. Now, you're probably feeling really skeptical about that, and I would be glad to talk about that more in class, and we'll also be doing a whole unit where we talk more about limits. Now, let's picture this geometrically. I think this will help you understand why this works. Let's picture a 1 by 1 square. And so the first term, 1/2, represents half of the area of the square. The second term, 1/4, represents 1/4 the area of the square. The third term, 1/8, represents 1/8 of the area of the square, and so forth. So this would be 1/16. This would be 1 over 32. This would be the next one, 1 over 64. This little piece right here would be 1 over 128. This little piece here would be 1 over 256. And you just keep going and going. And if you went infinitely, an infinite number of terms would fill the square. And the total area is equal to 1. So that's a geometric way of looking at a limit. All we can think of is in finite terms. It's just going to get really, really close to the filling up the square, and it's never going to get bigger than the square. But infinitely speaking, we say that it fills the square with an infinite number of terms. A stretch of the imagination, I know. Let's apply this to another situation. If we have a repeating decimal can actually be written as an infinite geometric sequence. So we can write this as 0.3 plus 0.03 plus 0.000, oops, one too many zeros, plus 0.003 plus 0.0003 plus, and so forth. And if we kept adding terms like this, and you might see it more easily if I wrote it like this, 0.0003, if we add those all together, you get 0.3333 and so forth, if we keep adding those. So this can be looked at as an infinite geometric sequence. And if we'd say, to get from one term to the next, we multiply by 0.1, because if you multiply by 0.1, it moves the decimal to the left one space. So this is times 0.1 times 0.1 times 0.1. You could also convince yourself of that by saying r is equal to 0.03 divided by 0.3 and so forth. So here we have 0.1. R is 0.1. Now we want to find the infinite sequence. So the limit as n goes to infinity, let me write s equals. I liked it better that way. S, the infinite sum, is the limit as n goes to infinity of s sub n, and that equals a sub 1 over 1 minus r. In this case, a sub 1 is 0.3, r is 0.1, 1 minus 0.1, so this is 0.3 over 0.9, which is 1/3. And hopefully you all recognize that 0.3 repeating is 1/3. So there's another example. Now why don't you try this next example and find the infinite sum for this. You can pause the video if you want and then turn it back on and see the answer. So here s is the limit as n goes to infinity of s sub n, which equals negative 100 all over 1 minus negative 0.8. And that's what you should have gotten for r, that r is equal to negative 0.8 by taking the second term dividing by the first, the third divided by the second, and so forth. That simplifies to negative 55.555 repeating. So that is the infinite sum. Now, something I haven't talked about is when is a sum not possible. So far, let me kind of help you remember that a geometric sequence can be written in a, or it can be graphed as a series of dots that have an exponential shape to them. So if r, since our formula for a term is a sub 1 equals a sub 1 times r to the n minus 1, r is the base. And if the base is less than 1, so r less than 1, we have a decreasing, I should say the absolute value of r, because if r is a negative number, yet like a negative number like -2, then this is not going to be the case. So we have a decreasing sequence. If r is greater than 1, we have an increasing exponential sequence. And so if it's increasing and we add an infinite number of terms, it just gets infinitely big. So here we have a situation where we have r is 2 times 2 times 2 times 2 times 2, r is equal to 2. So if we do, if we tried to use the formula, it would actually give us an answer, but it would be an incorrect answer. You cannot use the formula above if the absolute value of r is greater than 1. Okay, so you cannot use that formula. So this is a case, this is known as a diverging, let me spell that better. This is known as a diverging series. It diverges, in other words, it gets infinitely big. So this we cannot use the infinite sum formula for this one. That's the conclusion of this video.